So what we're going to look at today is we're going to look at something called the Laplace Transform. And the Laplace Transform is a very powerful mathematical tool that we're going to use in order to solve differential equations. What we're going to do first is we're actually going to first define the Laplace Transform. It's very standard ways or standard Laplace Transforms for different functions. Figure out how to find Laplace Transforms for different groupings of functions. And then we're going to use those in order to solve differential equations and look at some techniques that we can use in order to solve different kinds of differential equations. What you're going to find is that the Laplace Transform is really, really valuable and powerful for a lot of engineering applications. And that's one of the reasons why we're teaching them, is because you're going to see them lots of your engineering classes, or you may see them a lot in your engineering classes, especially if you're doing things like mechanical and electrical engineering. And so consequently, it's really important that you've actually been exposed to them, that you've seen them, and that you can use them. What you're going to find, what I think is going to be the case, is that once you get the hang of how Laplace transforms work, they're really not all that hard to use. And in fact, very, very versatile. And so hopefully you'll get a lot out of like this set of videos. Where we're going to start is we're going to start with the definition of Laplace transform. And so when we define the Laplace transform, we're going to say that f is a function defined on an interval from 0 to infinity. And the Laplace transform of f is the function f of s, big F of s. And you'll see it depending upon the letter of the function. It may be big X of s, may be big T of s. You know, it just depends upon the kind of function that we're using. And it'll be defined by big F of s is equal to the integral from 0 to infinity of e to the negative st f of t dt, provided that this improper integral actually does converge. And so what we'll do, we're going to see some instances in which we're going to have to restrict our bounds for s in order to make sure that the function does in fact converge. And you're going to see this notation a lot as well, and that is, and it's actually big L of f. And the big L stands for Laplace transform. F is the function that we're taking the Laplace transform of. This definition and finding this integral, it's important to know it, but you're not doing a lot of the integration. What we're going to be is going to be measuring the Laplace transforms for different kinds of basic sets of functions and then utilizing that in a lot of different scenarios. So you're actually not going to be doing a lot of integration here, which is probably great news for a lot of people. Heck, for me too. I prefer to do a ton of integration if I can avoid it. Let's look at an example of finding a Laplace transform now. This is probably going to be a good review for some of you as to finding the values for improper integrals. What do we do in those cases? And also just kind of a little review of integration by parts. So let's say, for example, we want to find the Laplace transform for 1. In this case, remember that our definition L of f is going to equal the integral from 0 to infinity of e to the negative st f of t dt. F of t in this case is going to equal 1. So the integral that we're going to have, L of 1, is going to equal the integral from 0 to infinity e to the negative st. We'll plug in 1 for f of t, so that's going to give us e to the negative st dt. Now this is an improper integral, so what we're going to be doing is we're going to take the limit semi-variable of n. The limit as n goes to infinity of the integral from 0 to n e to the negative st dt. When we go in and we integrate, we get the limit as n approaches infinity of, and this will end up being negative 1 over s e to the negative st integrated from 0 to n. This will then be the limit as n goes to infinity of negative 1 over s e to the negative st, or e to the negative sn, excuse me, minus negative 1 over s e to the negative s times 0. Now s here is a variable of some sort or another, okay? Or it's the variable that we're going to be using in our Laplace transform. So notice that it's not changing. That s is going to be there, and you're going to see that throughout the Laplace transform. Now this is going to end up giving me the limit as big N goes to infinity of negative 1 over s e to the negative sn plus 1 over s. Now notice that this is negative s. S, we're going to define it as actually being greater than 0. S will have to be greater than 0. If not, if s isn't greater than 0, this is not going to converge. So consequently, we need this fact that s is greater than 0 in order for us to have a convergent improper integral. So s will be greater than 0, and if s is greater than 0, then we're going to take negative s times n, let n go to infinity, and so this is going to end up equaling 0 plus 1 over s, and it'll just end up being 1 over s. And that's the Laplace transform for the function f of t equals 1. So there's our first example. Now let's find the Laplace transform for the function f of t equals t. Now what we have is we're going to have the Laplace transform for t is going to equal the integral from 0 to infinity of te to the negative st dt. And that will then equal the limit, and we'll use our dummy variable n going to infinity, again, 0 to n, te to the negative st dt. I'm going to then use integration by parts. So I'm going to let my, I'm going to have t, 1, 0, and then e to the negative st, negative 1 over s, e to the negative st, and then negative, or excuse me, positive 1 over s squared, e to the negative st. So this is going to then equal the limit as big N goes to infinity, the integral from 0 to n, or not, I don't need that any longer. I'm actually going to get negative 1 over s t e to the negative st minus 1 over s squared e to the negative st, and evaluated from 0 to n. This will then equal the limit as big N goes to infinity of this whole function, negative 1 over s te to the negative s, or excuse me, big N, e to the negative sn minus 1 over s squared e to the negative sn minus, and this will then be 1 over s times 0 times e to the negative s times 0 minus 1 over s squared e to the negative s times 0. And this will then be equal to the limit as n goes to infinity, negative 1 over s, n e to the negative sn minus 1 over s squared e to the negative sn, and then plus 1 over s squared. Now notice a couple of things, that if s is not greater than 0, then our integral in fact diverges. And you're going to see some conditions that we have for s, and they're all going to be based upon whether or not that integral is going to converge or not. And so consequently, we need to say that s is going to be greater than 0 so that the integral actually converges. Now notice, if we look here, we have n e to the negative sn. The exponential grows much faster than this n, and so this goes down to 0. That's going to go to 0. And then negative 1 over s squared e to the negative sn, that's also going to go to 0 as s is some constant. So this is just going to end up equaling 1 over s squared. And in fact, that's going to be the Laplace transform for the function t. And so both the Laplace transform for 1 and the Laplace transform for t kind of set up how it is that we would go about finding Laplace transforms if we actually had to start from scratch. What we're going to do in just a second is we're actually going to look at some basic cases or basic Laplace transforms that you're going to use over and over and over again, and then in future videos we'll use these cases without actually having to go through the whole integration. So now let's look at those standard Laplace transforms. We'll start out with the power functions, and the power function here we got L of t to the n, where n is some kind of constant, okay? And what we're going to get here is that this is going to end up equaling n factorial over s to the n plus 1. We already saw that with like t, where t is just t to the 1, and you'll notice that that's going to be 1 factorial, 1, over s to the 1 plus 1, or s squared, okay? So for example, if we did L to the Laplace transform t cubed, this will end up equaling 3 factorial over s to the 3 plus 1, and so that ends up equaling 6 over s to the 4th. And that's an example of utilizing a power function. One thing to note in case of the power function, in all cases, s is going to have to be greater than 0. Now let's look at exponential functions. Let's find the Laplace transform of e to the at where a is some kind of constant. The Laplace transform for e to the at is going to end up equaling 1 over s minus a. Pretty simple there. And actually, if you go in and you do the Laplace transform, you'll see this is how it works out. It works out very simply. And we just need to get that s is going to have to be greater than a in each and every case. So let's say, for example, I've got the Laplace transform of e to the negative 5t. That's going to end up equaling 1 over s plus 5. And we're going to need that s is going to have to be greater than negative 5. Otherwise, we end up having a divergent improper integral. What about some standard trig functions, especially those that you'll see a lot in sort of your engineering applications, like sine t and cosine t, or sine bt and cosine bt? So the Laplace transform for sine bt is going to end up being b over s squared plus b squared. And then again, s is going to have to be greater than 0. So for example, if I have the Laplace transform of sine 3t, that's going to end up equaling 3 over s squared plus 3 squared, which is 3 over s squared plus 9. And that's our Laplace transform. The Laplace transform for cosine t is going to be somewhat different, just a little bit different. It's going to actually be s. So it's going to be our variable s over s squared plus b squared. And again, s is going to have to be greater than 0. So take an example, L of cosine 5t. That ends up equaling s over s squared plus 25. And s, again, is going to have to be greater than 0. And so that is our Laplace transform for cosine bt. And so those are our trig functions. And pretty much we're going to be able to do an awful lot with functions, exponential functions, and our trig functions. So here's our list of standard Laplace transforms now. We'll have 1, t, t to the n, e to the at, sine bt, and cosine bt. All right, take a second, pause your video, make sure that you go in and write these down, and then what you're going to want to do is you're going to want to memorize them. Because in my next video, what I'm going to do is I'm going to show you how we use these standard Laplace transforms in order to do transformations without having to do any kind of integration. We're going to use the linearity of the integral and some facts about integration in order to actually do Laplace transforms quite easily for a really wide range of functions. Okay, so here are your standard Laplace transforms, right? Take a look at those. Take a look at the definition for the Laplace transform and how it is that we used integration by parts in order to find them. And that completes the video. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.